This is the second video about chemical reaction rates. In this video, we'll talk about how to find the rate from a data set. So in the video we just finished, we talked about the rate expression as the change in concentration over change in time. And I don't know about you, but this looks an awful lot like a rise over run, like the slope of a plot. So the rate can be found from the slope of a plot of concentration versus time. We'll put an exclamation point. We are always excited when we can find a variable from a plot. So it's concentration over time. So we need to plot concentration on the y and time on the x in order to find our slope. So here is a data set that I have pulled from the literature. Give you a second if you need to write this down in your notes. I'll hold. Okay, so here is our data set for this reaction. Hopefully you can read that. So bromine plus formic acid goes to bromide, protons, and carbon dioxide. And here are a few different measurements of the bromine concentration at a series of different points in the reaction. And then those points have been drawn on a plot to demonstrate how it changes over time. So here is our concentration of bromine plotted as our y variable. And here is our time over here on our x-axis. Okay, it's always good to familiarize ourselves with the axes of a graph before we get going. So what we said in the last video was what we really wanted more than anything else was to find the rate. And we said the rate must be the slope of a plot like this one, of a concentration versus time plot. But the problem here is this is not a graph of a line. If this was a graph of a line, it would be super easy to just pluck the slope right off the graph. However, this is not a line. This is more like a quadratic. It has kind of a curve to it. So we have a couple of different choices as to where we can get the slope from. So I'll tell you about them. There are 3 different choices we have. So the first choice is if we just say we can take the final point and subtract the initial point, and we can connect those with a line. Hopefully straight, depending on your art abilities. We're going to call that the average rate. For those of you who are taking calculus, that's called the secant line. So just connecting the first and the last point, that's the average rate. So let's calculate that for this data set. So here's our last point, 400 seconds, and here's our initial point at 0 seconds. We're going to do change in concentration over change in time. So we'll do the final concentration, 0.00296, minus the initial concentration, 0.0120. And we'll divide that by the change in time. So final time, 400 seconds minus initial time, 0 seconds. If you plug that into your calculator, you should get negative 2.3 times 10 to the negative third molar per second. And don't forget the negative, because this is a negatively sloped line. Okay, so one way we can do it is the average rate. Now the average rate is cool. It's definitely the easiest one to find from the data set. But if you notice, the slope of this line is about this, sloped. And that kind of matches what the slope looks like in the center of the line. But it doesn't really match what the slope looks like at the end. And it doesn't really match what the slope looks like at the beginning. So it's not very accurate when we're talking about the entire plot. So sometimes I want to find the slope at a particular point. And that's called the instantaneous rate. And for those of you who've taken calculus, this is called a tangent line. So we can take a tangent line to the curve where it only touches at one particular point. And we can do that by picking a point on either side and using those points to do rise over run. So I want to do this end of the curve. So I'm going to pick the last 2 points in my plot. Then I'm going to do rise over run for those. So I will do final concentration, 0.00296 minus initial concentration, 0.00353. And I'll divide it by the change in time, 400 seconds minus 350 seconds. And if you plug that in, you should arrive at negative 1.14 times 10 to the negative 5th molar per second. And if we compare those two numbers, this is a 10 to the negative 5th, and this number is 10 to the negative 3rd. Those slopes are different by a factor of 100. That is non-trivial. That is a pretty different slope. So you can see the reason why we'd like to do that. And finally, we use the points 400 and 350 in order to find our tangent line. So that means that this value is going to represent the slope in the middle of those two at 375 seconds. So right about here in between those 2 points. So this is called, I guess we'll write it in blue, instantaneous rate. There we go. And there's one more rate we can find on the graph, because we can find the instantaneous rate anywhere on the graph that we like. But there's one more point we're particularly important that we care about the most, and that is the initial point. We really care about what it first looks like when we first start. So we can draw a tangent line to the beginning, and when we draw that instantaneous rate at the initial point, it is called the initial rate. And I have now smudged this word, but it's okay. So we'll add that to our list. You can find the initial rate in the same way that you find the instantaneous rate. You just find the earliest possible instantaneous rate that you can. Those are our different options for slope: initial, instantaneous, and average. There's going to be a lot of data management going on in this chapter of the book. So stay with me and start to get used to looking at sets of data and making it work, figuring out information from it. There's one more thing I want to add at the end of this video, and that is factors that affect the rate, including the concentration like we saw in that plot of data. So one more baby section, factors affecting the rate. Okay, so there are 5 major things that affect the rate of the reaction, some of which we've already talked about, and some of which we'll talk about a little bit later in the chapter. So the first one is identity, which sounds obvious, but should be included in the list. If you are doing an acid-base reaction, for example, if you choose a different acid, the rate will proceed at either faster or slower. So the rate, I guess I shouldn't say it, the rate depends on the substance. Okay, the next factor that affects the rate is the surface area. And we aren't going to get into this one very much because we don't have a lot of time to talk about catalysts, but you should just know that when you are measuring the rate of something, you would need to have each of your different reactants in contact with each other. And so the greater the surface area, the more contact there is, and the more contact there is between reactants, the higher the rate. So the rate is going to be directly proportional to the surface area. The third factor affecting the rate is the concentration, specifically the concentration of reactants. When we made this plot and we looked at how the concentration of bromine changed and how the rate changed with it, we were only looking at this reactant. And that was because only the reactant concentration affects the rate. So usually, not guaranteed all of the time, but usually the rate is proportional to the reactant concentration. And we're going to talk about this in the next set of videos. Fourth factor affecting the rate is the temperature. You could probably predict how this works in your head. If you increase the temperature of a system, it makes the molecules move faster, and they collide with each other a little bit more often, like we talked about in the kinetic molecular theory section. And so usually, with more collisions and more heat in the system, it will increase the rate. So usually the rate is directly proportional to the temperature. We'll talk about this later in the chapter. And the final factor affecting the rate is the presence of a catalyst. You've probably heard about catalysts before, and if you have, you know that catalysts increase the rate of a reaction. So the rate is going to be higher with a catalyst. And we are going to cover this at the very end of the chapter. So that's an introduction to kinetics about what is rate, how do we get rate from data, and how do we express it as a rate expression. And in the next video, we will start to talk about rate laws, which are formal mathematical ways to talk about the rate of a particular reaction.